Steinhauer here. Welcome back. We are in this class taking our cosmic zoom lens, which has so far been focused pretty narrowly on the sun and other stars in the Milky Way galaxy. And we're going to very gradually over the last few weeks of the class zoom outwards and outwards and outwards and see how the universe is structured on ever larger scales. And that begins with the study of the galaxy as a whole, the one that we live in, the Milky Way galaxy. And so that begins chapter 25. Here you have an image of the Milky Way. If you've never gone out on a warm summer night away from city lights and looked up and seen on a clear night the Milky Way galaxy spreading out before you, you owe it to yourself to do it because it's one of the more spectacular sights you can see. You won't see it quite this bright or brilliant because this is an exposure that lasts some time, but it will, in the summertime, be possible to see what looks like bright patches in the sky. And what you're seeing is the disk of our own Milky Way galaxy. Now, of course, we can only look in one direction and see half of the sky at one time, but here you can see, this is the constellation Sagittarius. The center, when you're looking towards the constellation Sagittarius, you're looking towards the center of our galaxy. And you can see the disk of our galaxy spreading out in all directions, in fact, because we're located within the disk of our galaxy itself. And so if you've never done that, you owe it to yourself to go and look at the Milky Way galaxy. It's spectacular. Okay, here is an all-sky view. So again, you can never see all of this at one time while you're standing on the Earth. This is a full 360-degree view of it. Just kind of like you can't see the entire Earth at one time, even from outside, but you can unroll the Earth and place it down on a flat sheet of paper and see how it looks all at one time. You can do something similar with the sky and the Milky Way galaxy. Now, obviously, there's some distortions that you have to make, but the distortions are the smallest in the middle. And so if you put the Milky Way galaxy there, you can get a pretty good idea of what it actually looks like from 360 degrees. So again, in the middle of this, we're seeing the Milky Way galaxy. And as you move towards one side, this point and the point all the way over here are actually the same point. We've taken those two and unwound them and stretched it all out across the sky. And you can sort of see the components of the Milky Way here. We've certainly got a thin disk of material here. You've got kind of a bulgy part in the middle where it sticks up above and below the disk of the galaxy. And you can see lots of bright patches and very dark patches interspersed throughout the disk of the galaxy itself. Okay, so this is the actual view of the Milky Way. Sometimes it's easier to get a cartoon version of what's going on here. So here it is, the structure of the Milky Way galaxy. You've got the creamy nougat and the chewy caramel and the rich milk. Okay, fair enough. This is the Milky Way candy bar. What is the structure of the Milky Way galaxy? Here it is, the cartoon version. Again, we're seeing this edge on. So you've got this very thin disk, 1,000 light years or so in diameter. You've got the sun's location here, about 2/3 of the way out in that disk. Within there, you've got a bulge in the middle where things are moving in different directions and slightly different kinematically, and certainly extending up above and below the disk of the galaxy itself. And you've got the halo of the galaxy, which actually extends well beyond the limits of this image. And within that halo, there are objects like globular clusters that are denoted here by these dots. And so that is the true cartoon side view of what the Milky Way galaxy looks like. Now, we don't get this view of it, but if you could fly way up above the disk of the galaxy and look back down on it, you might see something like this. It's actually really difficult to study the Milky Way itself because we are embedded within it. We don't get the grand view like this from the top where we can just pick out the various pieces. It's the analogy that I like to use is it's sort of like studying the structure of a glass house that you live in when you're stuck in one of the rooms of that glass house. You can kind of see all the rooms, but they kind of run together, and it's kind of hard to tell which is which. But you have some clues, and your clues are other glass houses on the block that you can see from the outside and from different orientations. And you can make inferences about your house based on those other houses that you see and the things that you can see from your glass house. Anyway, if we could fly way up above the disk of the Milky Way galaxy and look down, it might look something like this. The disk of the galaxy looks very thin when you're in it, becomes this very nice circular shape with spiral arms and spiral structures embedded within it, the bulge in the middle that sticks up again, and this halo extending all the way around it that's more spherical in shape that contains those globular clusters. So the story of where we are in the galaxy is actually an interesting one. William Herschel in the 1780s was the first person to really try to solve this problem, and he did it by counting stars. And so here we are in this image, and he said, okay, let me look in this direction of the Milky Way galaxy, and I will count stars, and this direction, and this direction, and this direction, and he broke the sky up, and he just pointed his telescope in that direction, and he counted all the stars that he could see. And then he moved the telescope a little bit, and he counted all the stars that he could see there. And he moved the telescope a little bit, and he counted all the stars that he could see. And he made this map. And you can see there are certain regions where you can see a lot more stars, but for the most part, it's about the same in all directions. And his conclusion was that we must be in the middle of the galaxy. We must be at about the center of the Milky Way galaxy. Of course, we know that's not true today. And what he didn't understand was that there are things in the Milky Way galaxy that make it so that you can't see all that far within it. Those dusty lanes, those very dark regions of the galaxy are prohibiting light from traveling too far in the galaxy. And so all he was really measuring was how far you can see before you run into one of these very dark clouds. And so, yes, we're centered on that, but we're not centered on the Milky Way galaxy. Harlow Shapley in the 1910s was the first person to really get a handle on where we are in our own galaxy. And he did it by measuring the distances to globular clusters. We'll talk about ways of measuring distances to these nearby galaxies and globular clusters in a bit. He used variable stars. But the point is, if you can, it was already known that there were more globular clusters in one direction than the other, but he could also measure the distance. And he correctly surmised that these globular clusters are probably scattered randomly throughout the galaxy. And so if you can find the middle of the distribution of the globular clusters, you can find the middle of the galaxy itself. And he found that the middle, they centered on a point in Sagittarius. He didn't get the distance right, but he did for the first time realize that we were not in the center of the Milky Way galaxy, and that it must be quite a ways away towards the constellation Sagittarius. Okay, so let's talk about all of these components of the Milky Way galaxy, because obviously they form material components. In other words, the disk is separate from the bulge, is separate from the halo of the galaxy, but they are also kinematically distinct things. The disk of the Milky Way galaxy has stars that are all orbiting in the same direction and in roughly circular orbits. And so it's a very orderly, regular, ordered region of our own galaxy. You can see there's somewhat up and down motions, and this is simply caused by the gravitational force of the disk itself interacting on stars. But the yellow line you see here is an exaggeration of how far stars actually move in and out of the disk of the galaxy. They're, for the most part, moving in nice, constant circular orbits all in the same direction, which gives this very ordered spiral pattern to things. That is very different than the bulge and the halo. The bulge is this region here. Those stars in the bulge are not moving in any particular one direction. They're not all aligned in the same plane. They're not moving all in the same direction. And so they're fairly random. It's sort of like a hive of bees where they're swarming all over the place. Individual stars will be on regular orbits around the center of the galaxy, but the stars themselves don't have any particular pattern. This is why you get this spherical shape. And the same is true of the halo. In the halo of the galaxy, there is no preferred orientation. Stars and globular clusters and other things that are in the halo are orbiting in random directions. and sometimes on highly elliptical orbits that take them fairly close to the center of the galaxy and then fairly far away from the center of the galaxy. So kinematically, these three regions are quite distinct. The disk as opposed to the halo and the bulge of the galaxy. Okay, I want to next talk about the Milky Way and how it looks at different wavelengths, because we can get some important information about what the constituents of the Milky Way are by looking at it in different wavelengths. So here you see the visible part of the Milky Way. This is the image that we saw before. And in the visible, what are you seeing? You're seeing the stars in the Milky Way. Almost everything that you see that's bright is either a star or it's a nebula where stars are being formed. And in visible light, the images are blocked out by these, the view of the disk Milky Way is blocked out by these very dark clouds that dot the disk of the Milky Way and prevent us from seeing very far at all. If we look at the near infrared, if we go towards slightly longer wavelengths, those slightly longer wavelengths are able to penetrate through those dark molecular clouds much more easily than visible light is. So in the near infrared, 1 to 4 microns, we still see the surfaces of stars here, but now you see those dark lanes are pretty much gone because this light can travel fairly easily through them. And so you're seeing still these red regions are where those dark clouds were, but now you see a beautiful thin disk of stars and a slight bulge in the middle where those stars are moving in the bulge instead of in the disk. So different wavelengths of light, you're seeing different things. And here you can see where the stars are located physically in the galaxy, pretty much unimpeded by those dark clouds. If we go to the far infrared, further in the infrared, 60 to 100 microns, we're no longer seeing the surfaces of stars. We are now seeing where the gas is in the Milky Way galaxy. And you might notice the difference between this and this one, there is no bulge, first of all. The bulge is gone. There is no gas, interstellar dust in the bulge of the galaxy. This is the thin disk, a very thin disk of dust, gas and dust that occupies the center of the disk itself. And so this is seeing directly the gas and dust of the Milky Way. If we go to radio waves from carbon monoxide, it's a very similar story. You're seeing where the disk of the galaxy itself is and where those carbon monoxide, in this case, molecular clouds are. Here, these are the colder regions of the galaxy where you can actually form molecules, and those molecules can actually glow in the radio waves. Here is the radio from 21 centimeters. This is from hydrogen gas. This is from neutral, cold hydrogen gas. This is where the hydrogen in the galaxy is, again, confined to a very thin disk, thin plane that corresponds to the disk of our galaxy. When you go to the higher energy photons, like X-rays and gamma rays, you'll notice that the Milky Way disk now is dark. The disk of our galaxy isn't shining much in X-rays. And in fact, where the X-ray is coming from, these are very energetic, specific, very hot objects, like black hole binaries, like neutron star binaries. And so you can see you've got regions where there's bright X-ray sources, but these are individual objects within the Milky Way and not any sort of diffuse matter within the Milky Way itself. And gamma rays are even more high energetic. These guys, again, you're coming from, you don't have specific objects that are emitting many gamma rays. These are coming from atomic nuclei colliding very violently and emitting very high energy photons. But it's a very faint source. There aren't many of them there, but they do tend to lie along the disk of the galaxy itself. Okay, so that's the Milky Way in lots and lots of wavelengths. We'll come back in the next video and talk about other differences between the different components of the Milky Way galaxy.